In this video, we continue with the second part of chapter 6 on matrices as linear maps. In definition 6.5, we consider two vector spaces, V and W, over the same field F, and we call them isomorphic if there exists a linear map that we denote by a capital letter phi and which is bijective, meaning one-to-one and onto between the two vector spaces V and W. In this case, phi is called a vector space isomorphism. Recall that since phi is a bijective linear map, this means that phi is invertible and phi inverse is also a linear map. A few remarks about this definition. You may have heard the term isomorphism before, as it appears in many areas of mathematics. So you could think, for instance, of a group isomorphism in algebra and so on. The existence of an isomorphism between two spaces means that all important mathematical properties of the two connected spaces, in this case the two vector spaces V and W, are preserved. So for any type of vector calculations, for instance on the vector space V, we could use our isomorphism phi to bring all the data into the vector space W, perform our operations in W, and then use phi inverse to bring the results back into the vector space V. And what we get is exactly the same results as if we did the calculations in the vector space V. So hence, if V and W are isomorphic, we can think of them as being essentially the same vector space, because every calculation in V and W is paralleled by the other. For finite dimensional vector spaces, we now have the important result of theorem 6.6. So let V and W be two vector spaces over the complex field C, with the dimension of V being equal to n and the dimension of W being equal to m. Let B be a basis for the vector space V and C be a basis for the vector space W. Then we have the following two statements. A, V and W are isomorphic to Cn and Cm respectively. And B, any linear map L from V to W can be represented by a corresponding matrix A in Cm by n. So essentially what this theorem is saying is that any complex vector space of dimension n is isomorphic to Cn, and correspondingly a vector space of dimension m is isomorphic to Cm, and moreover any linear map between two finite dimensional vector spaces can be represented by a corresponding matrix. For the proof of theorem 6.6, we start with statement A, and we prove only the case for V here, as the case for W is analogous. Now consider an arbitrary vector small v in the vector space V. Since the set of vectors b1 through bn is a basis for the vector space V, there exists a unique set of scalars x1 through xn such that V equals to x1b1 plus x2b2 and so on plus xn/bn. Now consider the map phi that maps from V into Cn and which is defined by phi of V equals to the vector of the scalars that multiply the basis vectors b1 through bn. It's easy to verify that this map is in fact linear, one-to-one and onto, and therefore phi is the desired isomorphism. For the proof of part B of theorem 6.6, we first define the vectors w1 through wn in the vector space W as wi equals to the linear operator L of the basis vectors bi for all I from 1 to n. Since the set of vectors C1 through Cm is a basis for the vector space W, that means that for each vector Wi, there exists a unique set of scalars that we call A1i through Ami, such that the vector Wi equals to Lbi can be expressed as the sum over an index j that runs from 1 to m of the scalars Aj times the vectors Cj. Now pick any vector v in the vector space V and let the vector W be the image of V under the linear map L. Since the set of vectors Bi form a basis for V, there exists a unique set of scalars x1 through xn such that V can be written as the sum over the index I from 1 to n of xi bi. And similarly, since the set of vectors Cj form a basis for the vector space W, there exists a unique set of scalars y1 through ym such that W can be written as the sum over the index j from 1 to m of the scalars yj times the vectors Cj. By the way, the symbol of an exclamation mark stands for unique, so this quantifier here reads as there exists a unique. Now, when we put all of this together, what we get is the following. W is defined as LV. Now for W, we can substitute this sum, and for V, we can substitute this sum. And now, due to the linearity of the operator L, we can pull L inside of the sum, where the expression Lbi is exactly what we have defined as the sum over the index j from 1 to m of Aji Cj. Now we can pull the xi into this sum and exchange the order of the summation, and then we get the sum of the index j from 1 to m of the sum of the index I from 1 to n of xi Aji Cj. Observe that on the left-hand side, we have a linear combination of the vector Cj with the coefficients being the yj, and on the right-hand side also we have a linear combination of the vector Cj where the coefficients are given by these terms. And now, because the vectors Cj are linearly independent, we must have that the coefficients on both sides have to be equal. Notice that this is exactly the formula of a matrix vector multiplication, which can be written like this, and where we have this vector here as the representation of the vector v in the space Cn, and here we have the representation of the vector w in Cm, and here we have an m by n matrix that we can call A, and which is essentially a matrix representation of the linear map L. As a remark, it should be noted that theorem 6.6 holds analogously for real vector spaces, so where the underlying field is R instead of C. Moreover, for an illustration, there's a mapping diagram drawn down here, where we have the vector spaces V and W up here. Then we have an isomorphism called phi between the vector space V and the space Cn, and correspondingly an isomorphism called psi between the vector space W and Cm, and the linear operator L that maps between V and W has the matrix representation A between the complex spaces Cn and Cm. Our next topic is the change of bases. Note that for theorem 6.6, we have assumed that the vector spaces V and W have fixed bases B and C. However, as we know, bases for vector spaces are not unique. Hence, in theorem 6.7, we consider the vector space V with two different bases, B and B tilde, and the vector space W also with two different bases, C and C tilde. The statements of the theorem are as follows. A. There exist non-singular matrices T and R of appropriate dimensions such that x equals to T times x tilde, where x is the representation of a vector V in the basis B, and x tilde is the representation of the same vector V in the basis B tilde, and similarly y equals to R times y tilde, where y is the representation of any vector W in the basis C, and W tilde is the representation of the same vector W in the basis C tilde. And the second statement, B, is that we consider a linear map L from the vector space V into the vector space W. And we suppose its matrix representation with respect to the bases B and C is given by the matrix A. Then its matrix representation A tilde with respect to the bases B tilde and C tilde is given by the formula A tilde equals to R inverse A T. For the proof of theorem 6.7, part A, it's known from theorem 6.6 that the following mapping diagram exists. Between the vector space V and the space Cn, there exist two vector space isomorphisms, phi and phi tilde, that correspond to the bases B and B tilde. So for any vector V in the vector space V, we get two different representations, x in Cn and x tilde in Cn, based on the isomorphisms phi and phi tilde. What we need to prove is that there exists a n by n matrix T that maps x tilde to x, and that this matrix T has an inverse matrix, T inverse, that maps x to x tilde. Now pick any arbitrary vector V in the vector space V. By the definition of the isomorphisms phi and phi tilde in the proof of theorem 6.6a, we have that V can be written in terms of the basis vectors in the basis B by summing from j equal 1 to n of the elements xj of the vector x times the corresponding basis vector bj, and alternatively we can express V in terms of the basis B tilde by summing from I equal 1 to n of the elements x tilde I of the vector x tilde times the corresponding basis vector B tilde I. Note that we can also express each of the basis vectors in B tilde in terms of the basis B. So we can express a basis vector B tilde I as a linear combination of the basis vectors in B, where the variables tji denote appropriate scalars. And we can substitute these expressions into the formula up here. Then we can exchange the two summations over the index j and the index I, and we get to this formula down here. Now, the vector on each side of this equation is expressed as a linear combination of the basis vectors bj, and since the basis vectors bj are linearly independent, that means that the coefficients on each side have to be equal. And that's exactly what's stated here. So the coefficient xj must be equal to the the sum of I equal 1 to n of x tilde I times the scalar tji, and this equation must hold for all j from 1 to n. And this, of course, is mathematically equivalent to saying that x, which is the vector of the elements xj, is equal to a matrix T times x tilde, which is the vector of the elements x tilde I, and the matrix T is defined as having the ijth element being equal to tji. For the existence of T inverse, note that T can be written as the combination of phi with phi tilde inverse according to the mapping diagram at the beginning of the proof. Hence, T is bijective and therefore invertible. The proof for y being equal to a matrix R times y tilde is of course analogous. The proof of part B of the theorem is now almost self-explaining by just drawing the complete mapping diagram. So we have the vector spaces V and W and the linear map that maps from V to W. Then for the vector space V, we have the two isomorphisms phi and phi tilde according to the basis B and B tilde, and which make V isomorphic to Cn in both cases. And we have the n by n matrix T, which maps between the two spaces Cn and Cn. On the other side, we have the same thing for the vector space W. So we have two isomorphisms psi and psi tilde according to the basis C and C tilde, and which make W isomorphic to Cm in each case. And we have the m by m matrix R that maps between the vector spaces Cm and Cm. Hence, for an arbitrary vector v in the vector space V, it has a representation x tilde in the basis B tilde and a representation x in the basis B, and its image under the map L, LV, is an element of the space W, which has a representation in the basis C tilde, which is called Y tilde, and a representation in the basis C, which is called Y. So reading directly from the diagram, we get that x equals to t times x tilde and y equals to ax, meaning that y equals to atx tilde. And finally, y tilde equals to r inverse y, and hence equals to r inverse atx tilde. So therefore, the matrix representation of the linear operator L with respect to the basis B tilde and C tilde is given by this matrix, which we call A tilde. Now we proceed to the very fundamental definition 6.8 of the range space and the null space. So let L be an arbitrary linear map from the vector space V into the vector space W. Then the range space of L, denoted with a calligraphic R, is the set of all y in the codomain W such that there exists an x in the domain V with Lx equals to y. The null space of L, denoted with a calligraphic N, is the set of all x in the domain V such that Lx equals to 0. What's important to note is that the range space is a subset of the codomain of the linear map. The null space, on the other hand, is a subset of the domain of the linear map. Therefore, the range space and the null space of a linear operator can generally not be compared because they live in different vector spaces, unless V and W happen to be the same vector space, which is an important special case that we will consider in detail in a later part of this lecture. Now, for a few more remarks about definition 6.8, it is easy to verify that the range space is indeed a subspace of the codomain, and the null space is a subspace of the domain of the linear operator L. So this is left as an exercise. Clearly, it's just a tautology to say that L is surjective if and only if the range space of L equals to the entire codomain, and L is injective if and only if the null space of L is just the zero vector. It's also easy to see that if the linear operator happens to be a matrix, then the range space of this matrix equals to the span of the column vectors in this matrix. And you can see this by just looking at the mechanics of matrix vector multiplication. Now we have the very important theorem 6.9 about the range space and null space of a matrix A and its adjoint matrix A star. In particular, the following spaces are equal: A, the orthogonal complement of the range space of A equals to the null space of A star. B, the direct sum of the range space of A and the null space of A star equals to Cm. C, the null space of A star A equals to the null space of A. And D, the range space of A star equals to the range space of A. So let's look at the proof of theorem 6.9, beginning with part A. Let X be any vector in the null space of A star. By definition, this is equivalent to saying that A star X equals to 0. This, in turn, is equivalent to the inner product of A star X with Y being equal to 0 for all vectors Y in Cn. Now, by the definition of the adjoint map in the first argument, we can replace it with the map A in the second argument. The inner product of X with AY being equal to 0 for all Y can also be written as X being orthogonal to AY for all Y. But now this side here corresponds exactly to the range space of A, so we have that X must be orthogonal to the range space of A, and this means that X must be in the orthogonal complement of the range space of A. And since all the steps that we have made are bidirectional, we're done with our proof, and we can conclude that the null space of A star equals to the orthogonal complement of the range space of A. For part B, note that by lemma 525D, we can write the space Cm as the direct sum decomposition of the range space of A and its orthogonal complement. But in part A, we have already proved that the orthogonal complement of the range space of A equals to the null space of A star, so we're done with part B. Part C will be proven in two parts. What we have to show is that the null space of A is equal to the null space of A star A, and we first show the set inclusion in this direction. To this end, let X be in the null space of A, which means that AX equals to 0, and therefore, of course, also A star AX equals to 0, which means that X is in the null space of A star A. Secondly, we also have to show the opposite set inclusion, and to this end, we assume any vector X in the null space of A star A. So by definition, this means that A star AX equals to 0, and therefore also X star AX must be equal to 0, which implies that the square 2 norm of ax equals to 0, and this in turn implies that ax equals to 0, so x is in the null space of A. Now for part D, where we have to show that the range space of A star equals to the range space of A, we again split the proof into two parts, and we first show the set inclusion in this direction. To start, assume that y is in the range space of A star, which by the definition of the range space means that there exists a vector x such that y equals to A star x. And now we can define the vector A star x as a new vector x tilde. Then the statement clearly implies that there exists a vector x tilde in Cn such that y equals to ax tilde. And now this is exactly the definition of y being in the range space of A. The opposite set inclusion, that the range space of A is a subset of the range space of A star, is a little harder to prove. First, note that the space Cm can be written as the direct sum decomposition of the range space of A star and the null space of A star, and that's by part B of this theorem. And this in turn can be written as the direct sum decomposition of the range space of A star and the null space of A star by part C of this theorem. Now pick any vector y in the range space of A with the purpose of showing that y is also an element of the range space of A star. By virtue of the direct sum decomposition in definition 417, there exists a vector s in the range space of A star and a vector t in the null space of A star, such that y can be written as the sum of s plus t. By assumption, y is an element of the range space of A, and s is an element of the range space of A star. By the first part, however, we know that the range space of A star is a subset of the range space of A, so S is also an element of the range space of A. Therefore, solving this equation for t yields that t is equal to y minus s, so the difference of two vectors in the range space of A, and hence t itself, must also be an element of the range space of A. Thus, we have that t is in the null space of A star and t is in the range space of A. But by part A of this theorem, the null space of A star equals to the orthogonal complement of the range space of A. Now, t is in the orthogonal complement of the range space of A and at the same time in the range space of A, and therefore the vector t has to be equal to 0. So with t equal to 0, what remains of this equation is y equals to s, where s is an element of the range space of A star, and therefore y has to be an element of the range space of A star. Based on the definition of the range space and the null space, we have definition 6.10 of the rank and the nullity of a matrix. Namely, the rank of a matrix is the dimension of its range space, and it's denoted as rank of A, and the nullity of a matrix is the dimension of its null space, denoted as nullity of A. For some important properties of the rank and the nullity, we have theorem 6.11. So let A and B be two matrices of appropriate dimensions. Then A, the rank of A equals to the rank of A star. B, the rank of A is less than or equal to the minimum of its dimensions m and n. C, the rank of A plus the nullity of A star equals to the first dimension m. D, the rank of A star plus the nullity of A equals to its second dimension n. E, the rank of A equals to the rank of A star equals to the rank of A star A. And finally F, we have Sylvester's inequality, which states that the rank of A plus the rank of B minus n is less than or equal to the rank of AB, which is again less than or equal to the minimum of the rank of A and the rank of AB. For the proof of theorem 611, we start with the easy parts, which are parts C, D, and E that follow directly from theorem 6.9, parts B and D. For part A, we prove the identity that m minus the nullity of A star equals to n minus the nullity of A, so the result follows immediately by observing parts C and D, which we have already proven. The proof of this identity will involve two parts. In the first part, we will prove this sided inequality, and in the second part, we prove the opposite inequality. So let the set be 0, consisting of the vectors b1 through b new, be an orthonormal basis for the null space of A, which always exists because the null space of A is a vector space, and hence it has a basis, and hence we can use the Gram-Schmidt procedure to make this basis orthonormal. Here, the Greek letter nu is used to denote the nullity of A, which was defined as the dimension of the null space of A. Hence, the basis contains exactly nu basis vectors. Then extend B0 to an orthonormal basis B for the entire space Cn, which is always possible by virtue of the Steinitz replacement lemma and the Gram-Schmidt procedure. So what we now have is a set of vectors b1 through b new and b new plus 1 up to bn, such that a bi equals to 0 for the first new vectors, and a bi is non-zero for the following vectors nu plus 1 up to n. According to theorem 6.9c, any vector bi is in the null space of A if and only if bi is in the null space of A star A. Therefore, we can also write that A star A bi equals to 0 for the first new indices, and A star A bi is non-zero for the indices from nu plus 1 to n. Now we define the vectors ci as a bi for all indices I greater than or equal to nu plus 1. And we claim that this set of vectors ci is linearly independent. To show this, we take any linear combination of the vector ci and put it to 0. And what we need to show is that this implies that all of the scalars alpha I must be 0. Now we substitute the definition of the vector ci, which says that they're equal to a bi, where we can now pull the matrix A out of the sum, where we observe that the remaining sum represents a vector in the orthogonal complement of the null space of A for all choices of the scalars alpha I. And therefore, the only way for this expression to be 0 is for all of the alpha I to be equal to 0. Hence, what we have found is n minus nu linearly independent vectors which are in the orthogonal complement of the null space of A star. And therefore, the dimension of the orthogonal complement of the null space of A star is greater than or equal to n minus nu. Finally, with the observation that the dimension of the orthogonal complement of the null space of A star is equal to m minus the dimension of the null space of A star, which is the nullity of A star, and with remembering that nu was defined as the nullity of A, we get exactly the desired inequality. For the opposite inequality, we can just repeat the proof of the previous inequality with A star in place of A. And thus, the proof of part A is complete. Part B now follows immediately from part A together with parts C and D. And finally, the proof of part F of Sylvester's inequality is omitted here. So we have completed the proof of theorem 6.11. On this slide, we have two more lemmas which are very useful in practice. First, lemma 6.12, where A is any m by n matrix and Q is an n by n matrix that is invertible. Then the range space of A equals to the range space of AQ, and therefore also the rank of A equals to the rank of AQ. The proof of lemma 6.12 will be part of the next exercise sheet. Then after lemma 6.12, here's a little question for you to think about. So let A be an m by n matrix and P be an m by m matrix that's invertible. Is it also true that the range space of A equals to the range space of P times A? And what about the rank of A being equal to the rank of P times A? The second useful result on this slide is lemma 6.13, where A is defined as an n by n matrix, and the lemma is then stating that the following three conditions are equivalent. A, the matrix A is invertible. B, the null space of A equals to the zero vector, or alternatively the nullity of A equals to 0. And C, the range space of A equals to the entire space Cn, or alternatively the rank of A equals to n. We will prove lemma 6.13 by showing that A implies B, B implies C, and finally C implies A. First, to show that A implies B, pick any x in the null space of A, which means that A times x equals to 0. Now we can multiply this equation by A inverse on both sides, because by the assumption of part A, the matrix A is invertible. This, of course, is equal to the identity matrix, hence what we get is that x is equal to 0. The result that any vector x in the null space of A equals to 0, of course, implies that the null space of A must be equal to the 0 vector. Second, for B implies C, we use theorem 6.11d, which says that the rank of A star plus the nullity of A equals to n. Moreover, by theorem 6.11a, we have that the rank of A star equals to the rank of A, and by assumption we have that the null space of A equals to the 0 vector, and hence the nullity of A equals to 0. Therefore, it's clear that the rank of A must be equal to n, and the range space of A must be equal to the entire space Cn. Third, for the proof of C implies A, we have by assumption that the range space of A equals to Cn, and therefore solutions x1 through xn in Cn must exist to the following systems of linear equations. In the first system of equations, x1 is the solution to ax1 equals to the first unit vector. In the second system of equations, x2 is the solution to ax2 equal to the second unit vector. And we continue in this fashion up to xn, which is the solution to the equation system axn equals to the nth unit vector. And these solutions must exist because all of these unit vectors are in the range space of A. Now we can combine these vector equations into one big matrix equation where we multiply the matrix A with the matrix that we get if we list the column vectors x1, x2 up to xn in one big matrix, and this yields the list of column vectors on the right-hand side, which is nothing but the identity matrix. So what we have found is an explicit expression for the inverse of A, and therefore we can conclude that A must be invertible.